Year 11, welcome to the second online learning session for GCSE Chemistry. Today's session will be delivered by Mr. Stevens, who's an examiner for the WJC. In today's session, you'll be viewing the reactions of acids. My name's Mr. Black, and I'll be available in the chat to answer any of your questions you might have during the session. I'll now pass you over to Mr. Stevens.
Good evening. Right. I'm going to go back through the basics, introduce you to a few kind of trigger words that I teach my own kids, just because I find it's quite useful for them, and just run you through the basics of the four classic reactions that acids undergo, and then if time allows, we proceed and use that knowledge to delve a bit into how you can use those reactions to prepare certain salts. Okay, so if I just go through the initial few slides with you. Okay, so it's things like common acids. Now you've carried this from Key Stage 3 and certainly through year 10 and year 11. You've come across a lot of common, what we'd call mineral acids. So you've got the classic hydrochloric acid, sulfuric acid, and probably depending on your teacher, I find over my experience, you might be maybe familiar, maybe not quite so familiar with the third mineral acid that you're expected to be familiar with, which is nitric acid. Okay, now unlike in Key Stage 3, where you've got that luxury of just having to know their name, you have to know the name and the formulas of these off by heart in Key Stage 4. Okay, so in this unit, you would have had to be familiar with HCl, which is hydrochloric, H2SO4, and HNO3. Now, the common thing you'd have noticed in those formulas would be the presence of hydrogen ions. Okay, so all of them contain hydrogen because that links in, if you're doing higher tier work, to the fact that an acid is defined or described as something that has the capability of giving a proton or hydrogen ion away. Okay, so something that just never goes away in GCSE chemistry, unfortunately, it rears its ugly head in every unit you do from the beginning of year 10 through to the end of year 11, is that you have to be able to produce unbalanced chemical symbol equations. Okay, even in foundation tier, they're not as common in foundation tier units, but they are still expected of you to be able to produce these chemical balanced equations. Okay. Just to recap there, it plays a key part, more so, I suppose, in the preparation of salts. That's the latter part of this PowerPoint, is that if you come across the state symbols GS, L and AQ, that you're kind of comfortable with what they mean. So it's like gaseous, so a gas, a solid, a liquid. And aqueous means dissolved in water, which kind of goes across to what Mr. Black was referring to last week when he was doing the ionic kind of structures and how they will dissolve in water and often do so. Okay, so that would be called aqueous. Now there are a few links there if you're not overly confident possibly in balancing equations and how to prepare them. There's just a few YouTube clips that we've included there just so that you can practice independently if that's something you want to do. Okay. So by the end of this, I'll just hopefully have got you to be a bit more familiar with the term bases, alkalis. There's a discrete difference between them, but they pretty much undertake the same type of reactions. So metals, metal oxides or bases, metal hydroxides and carbonate as well. Those are the four standard equations and four standard reactions I'll be touching upon. Okay. Hopefully you'll be able to then confidently be able to write equations, both words and symbols. And for the higher one, and I'll be honest at the beginning, it's best to be, I doubt I'll get to that bit of the presentation, but it will be there for you to kind of mull over at your own discretion after this session tonight. Okay, so just go back to very basics. Okay, acidity and alkalinity. So in year 7, 8 and 9, we just called them acids or alkalis. Didn't really delve into what they meant possibly, but most of you had been quite comfortable in at least identifying what they mean. So we've developed that in GCSE certainly now to be able to more confidently say that an acid is the presence of H+ ions, so hydrogen ions. We also call them protons. Okay, and hydroxide, something you've probably handled in the laboratory. I know that year 8 and 9 with me often do this kind of simplistic practical where they use sodium hydroxide in the laboratory. So you might have heard of things like sodium hydroxide. So that is OH minus. That will give a solution alkalinity, or will give it a pH that is on the upper scale, so above 7. Okay, so you can either have a acidic solution, an alkaline solution, or in the case of pure water, you can have a neutral solution. Okay, indicators also something you carry through with you from key stage 3. Now, that doesn't mean that it's no more important, but you've probably come across indicators very early on in comprehensive or secondary school. So these are substances that will allow you to predict, or at least give a sensible value for a species, so whether something is acidic or whether something is alkaline, or very rarely actually whether something is neutral. Okay, some will even go that bit further and tell you how acidic or how alkaline a solution is. So in year 7 we start with the basics, so we allow them we let them loose on litmus in year 7. I'm sure you all were as well. Now that means if it's acidic, it's red. If it's alkaline, it's blue. Rarely known fact that litmus, if it's neutral, it's actually purple. Okay, so universal. This is the one that most people think just is the standard indicator in the laboratory. So it's the one that gives you a nice range of different colours. So you've got the range from acidic, which is red, all the way up to the kind of purples or violet coloration of alkaline solutions, and then you've got the green indicator in the middle there, which most people recognize because that's the color of the indicator itself. Okay, so you get green universal indicator, which is indicative of neutral. So having a good sense or an idea of the rough pHs of everyday things will do you great kind of good things. Okay, so having the idea of certain things like stomach acid, milk, blood, things that you're familiar with, and having a sense of what sort of pH they are, and being able to sensibly justify what pH they are, it's probably something I would advise you do. Okay, so it ranges there from 0 to 14. Okay, most examiners will accept the range being 1 to 14, but it's in fact 0 to 14. Okay, you've got the fact that over the time of your life, I'm hoping that you've been taught that fizzy drinks aren't particularly good for you, that fruit juices aren't particularly good for you. And the reason they're not particularly good for you is because of the content of the acidity. So you've got their lemon, which has a pH of around 2 to 3. Okay, coffee is acidic as well. Okay, blood is ever so slightly alkaline. It's probably slightly alkaline due to the presence of iron. So linking into a bit of your biology there, it contains hemoglobin, doesn't it? Which is metallic, and a metallic presence does tend to push it into that alkaline region. Okay, but sense should tell you, okay, that it isn't sensible to have something superbly corrosive. Okay, so if it's something that you ingest or eat or you put directly onto your skin, it's unlikely to be massively away from that central point of 7. Otherwise, it would be dangerous. Okay, so having just an overview, a bit of a gut instinct about certain substances and what pH they are is probably a sensible idea. Right, so as I say, and the next slide will probably either make you think that I'm a bit batty, or you'll go, oh, somebody said that to me once, or that's a good idea. So there are 4 classic reactions: acid and metals, acid plus metal hydroxides, metal oxides, and carbonates. Now, I always start with trigger words for my pupils here, be it the foundation all the way up to the higher, and they do tend to, once they get over the fact that I'm making up words that don't exist in their vocabulary, they remember them. Okay, and once you remember something, it doesn't matter why you remember it, remembering it is met its purpose then. Okay, so these are the trigger words that I teach my pupils. Okay, and I've even seen it, so I can't be the only batty person in Wales that does it, because I've seen it scribbled in pencil on exam papers when I mark occasionally. Is that the trigger word for the first reaction is MASH. Okay, so that stands for metal plus acid gives salt plus hydrogen. Okay, and that's because every single one, if you look at that summary there, the common denominator in all of them is that all of them have an S, because every single reaction you are expected to recall does in fact have salt as one of its products. It's that kind of common denominator there. Okay, all of them produce a salt of some sort. So the metal one, MASH, is the trigger word. Metal plus acid gives salt plus hydrogen. Then you've got azu, but you have to say it funny. You have to go azu because it's two A's. Okay, and the reason that is because a metal hydroxide is more commonly known as an alkali. So it means alkali plus acid gives salt plus water in this case. You've got bazu, a metal oxide. And I've just realised I have a typo in my slide. I'll change that before it gets sent out to you, but I might be able to change it on this so that I'm not totally confusing some of you. Is that a metal oxide? I just scrapped that out. Apologies to my lovely pupils. Okay, so a metal oxide is known as a base. Okay, so the trigger word my pupils get taught is bazu for that one. Okay, and then metal and a carbonate is called the trigger word, and it is a made-up word, but I really guarantee that every one of my year 11s will be able to regurgitate it, is cascu. So my year 11 pupils, as always, will be able to tell you mash, azu, bazu, and cascu. Okay, if you have some sort of trigger word, it will just help you be able to recall the kind of correct equation at the correct time. Okay, and it stops you confusing the products of what it makes. So if I go to the first one, MASH, okay, it's really important here that you have a sense of what you're looking for as well, okay, because one of the common questions that might creep up is what sort of observations would you expect to see? Okay, so if I go back to the fact that my trigger word here was MASH, okay, it tells you that H is made. Okay, now I'm hoping that you're all comfortable with the fact that hydrogen is a gas, so you'd expect to see bubbles, wouldn't you? So it says there, what do you notice happen when you put magnesium ribbon in an acid? Okay, well, it fizzes. Yet again, don't get kind of hung up on certain vocabulary being right or wrong. As long as it's scientifically correct and it addresses the question, then it's fine. Okay, so it says that you might, one people might say effervescence, one might say it bubbles, some might say it fizzes. What is worth saying, okay, and this is the one wrong answer that as examiners we're not allowed to accept, is the answer what's wrong with that? Makes hydrogen. You've just said it makes hydrogen. Well, the key difference that the examiner or chief examiners told us as examiners we're not allowed to give credit for that is that you have to make clear that that hydrogen does not dissolve into that solution and you physically see bubbles being made. So making something doesn't necessarily get you the credit. So be careful, okay, year 11, that when you say makes hydrogen, that you're clear that that hydrogen will then appear as bubbles or as effervescence. Okay, saying it makes hydrogen isn't good enough. And I do feel every year if somebody says that, I feel bad giving them a big fat cross, but that's the reality. Okay, we've been told not to accept that kind of probably ambiguous kind of description of it makes this. You have to say an observation, which in this case is the bubbles. Okay, hydrogen is one of the classic gases that you're meant to carry through with you from Key Stage 3 somewhat and know how to test it. It's the classic popping expectation. Okay, so you can see there that when you put a lit splint into that gas, it would make that squeaky pop, and that is evidence that that gas is hydrogen. Okay, so probably not the time to dwell on it too much, so I won't say too much on this point, but don't forget the classic test. So oxygen relights a glowing splint. Okay, hydrogen burns with the squeaky pop. I'm not sure the squeaky is essential, but it burns with a pop. And then you've got the carbon dioxide that turns lime water milky. So those are classic gases that you're meant to be able to give a classic test for. Okay, right. So moving on, okay, acids plus metals, okay, this is true for any metal reacting with any acid, except, okay, carrying through from what you will do in another unit, which is the metal unit that traditionally follows this. Some metals will not react with an acid, okay, because of the fact that it's not as reactive as you'd want it to be. So the lower reactivity metals, things like gold, silver, even copper, believe it or not, doesn't react with acid. Okay, so be careful thinking that this is true for every single acid. But for the purpose of this evening, if you just learn any acid and any metal will make these two products, which is a salt and hydrogen. Okay. Now, you can see there's a word equation. Now, the word equation tends to be, okay, always asked in foundation and sometimes built upon into the higher foundation papers as well. So if you say there, sulfuric acid and magnesium, mix magnesium sulfate and hydrogen, okay? What I'd like you to draw your attention to there is that the salt, in this case, this is the salt. So from the mash, okay, that's the salt that we're talking about, okay? The salt originates its name from two bits of information given on the left-hand side. So those are the reagents, okay? So if you think about what you see on that left-hand side, the two clues needed to name the salt are already there, because the name of the salt has two rules to it. Always starts with a metal or a metallic element, okay? So the name of the salt is always going to be whatever metal appears on that left-hand side. And then the second part of the name is just a rule you're going to have to learn, okay? And it originates from the nature of the acid. So if you have one sort of acid, it will make one type of salt. If you have another acid, it makes another salt. And the rules are as follows. If the acid is hydrochloric acid, okay, the salt always has it's called the suffix. Let's use everyday word, has the ending, okay, chloride. So if the hydrochloric acid, it makes something chloride. If you're using sulfuric acid, it makes something sulfate, okay? Nitric, the third one that probably a bit less familiar to you, makes something nitrate, okay? This rule is the same for any salt. So as I said earlier, the common denominator in all the equations was that S. Every one of the four equations I'm going to go over with you this evening has salt as a product. So this rule for naming a salt, okay, this here is a rule all the time, okay? So doesn't matter whether we're on the MASH trigger word or whether we're on the Casco trigger word, the rule is always the same. Treasure hunt a metal somewhere, look for a metal. That's the beginning of the salt name. And then look at what the acid is and apply the correct ending. If it's sulfuric, add the word sulfate. If it's nitric, add the word nitrate, okay? So if I just give you three quick examples there, and I'm going to stop talking, which is a rarity for me, okay? Just for, I don't know, 10 seconds, just so you have process the time yourself, okay? Look at them, what do you reckon the products are, okay? If you've got paper in front of you, scribble down your own ideas. Doesn't matter if it's right or it's wrong, okay? Because by the end of it, I hope we'll correct any errors you have, or we'll reinforce the understanding if you got it correct, okay? Whilst I'm just going to pause and not talk too much, this is just a link to the table of ions. Don't forget, they give you this in every exam, okay? They always list the ions. You don't have to memorize the ions, okay? So once you've got the ions, which is always going to be, if you were sitting a normal exam, would be in the back, but if I'm sure all of you will be having access to these if you're doing internal little tests in school, okay? They're going to have to give you the ions. You don't have to remember them, okay? So if I go back to this one, okay, what do you reckon those equations are? Okay, remember the rules I said? Treasure hunt for a metal. Well, look, All of these are metals. Okay, so it's a case of look for the metal. I've got a metal there. I've got a metal there. Okay, so the first part of the words is always going to be lithium. It told you that it was sulfuric acid. Okay, and if you go back to the previous one, sulfuric acid means it's something sulfate. So, hey presto, the product is going to be lithium sulfate. Yeah? Same thing for the second one. You've got sodium. Okay, not that I suggest anybody adds sodium to hydrochloric acid, but the theory is the same. Okay, sodium plus hydrochloric acid makes the salt sodium chloride then, because it makes hydrochloric acid is a chloride. And then the third one, which is safe to do in the lab, you've got magnesium nitrate, because nitric acid gives the salt nitrate at the end. Okay, common denominator though in all of them is that all of them will make hydrogen as a byproduct. Okay, so all of them produce and stick to the trigger word MASH. All of them make a salt, all of them make hydrogen. And that's always going to be the case. Okay. Right, the second one you have to be familiar with is metal hydroxides or the alkali. So this is the Azu one. Okay. So metal hydroxides are usually dissolved in water. So for example, sodium hydroxide that most people are familiar with, it's actually a white solid, but you never see it as white solid because you get given by your teacher the solution, this colorless solution that is labeled sodium hydroxide. Okay, so they're colorless usually. So metal hydroxides are commonly called alkalis, as I said, hence the trigger word being Azu. Okay, sounds like you got a bit of stutter, but it's a way of you remembering the trigger word. Okay, and as is the case, and you're already familiar with it maybe, it's a reaction that's classified as neutralization. Okay, the most common example of an alkali, as I said earlier, is sodium hydroxide. You mix that with hydrochloric acid and it makes common salt. So I mean the salt you put in your chips. It makes sodium chloride, okay? But just to hone in on this trigger word here then, the key word, neutralization. Now that is something you might have heard of already, but it's something that is quite important that you recognize when it happens, okay? So neutralization, if you think about that pH scale I referred to in one of my earlier slides, if you take something from this, so let's say I take something that's pH 2 and add something that's pH 13 to it, what will happen is that they will meet halfway and give you a neutral solution. So you take an acid, add to it the opposite, which is a base or an alkali, and you'll produce something centrally, therefore neutralized. So you get a neutral product as a result of that. Okay, so if you start with hydrochloric acid, if you add sodium hydroxide to it, so you got those, I couldn't get the perfect colors, but if you get the colors purple added to something that's pH 1, which is usually red, okay, what will happen, okay, is that eventually they will neutralize and creating the salt sodium chloride, which is neutral and pH 7. Okay, so it's important that you recognize neutralization when it occurs. Okay, right. Second equation in a bit more detail then is the Azu, as I said. Same pattern again. It's not a simple metal this time. It is a metal, if you notice, a metal hydroxide. I want you to kind of focus somewhat of the fact that it's a metal hydroxide and just remember that there is a metal. Don't forget, it's a treasure hunt all the time. If you look at the left-hand side, look for a metal. There will be a metal there somewhere if it is a neutralization reaction. Okay, so in this case, it is just focusing on the fact that it is sodium, focusing on the fact that it's nitric acid, and as a result, it makes the salt sodium nitrate. So it's the same rules again. You're looking for a metal and you're adding either the finishings of chloride, nitrate, or sulfate. It's going to be one of them endings for the salt. Okay. So yet again, formed from the name of the metal and from the acid by just combining them. So every slide I've reminded you of this rule, okay? Right, yet again, let's have a think. What could possibly the products be of these? So you've got sodium hydroxide and hydrochloric acid. That's the one I won't dwell on too much because that's the one I told you would happen. So it's sodium hydroxide and hydrochloric acid makes sodium chloride, which is the common salt you put in your chips, and water. Lithium hydroxide. Notice each of these has this. It's probably a good opportunity just to stop and remind you, if you see one of the reagents has the ending hydroxides, I want that to be the moment that light bulb goes off and you think, right, hydroxide, that must mean I'm now dealing with the azu trigger word. Hydroxide is the word that's going to tell you you're dealing with an alkali. If you're dealing with an alkali, the trigger word you meant to have recalled after tonight is azu. So acid plus alkali gives salt plus water, azu. Okay, so that's the trigger word for you to remember. If it's a hydroxide, I'm thinking about an alkali. Okay, so lithium and hydroxide there, and nitric. So we've suddenly changed the metal. So we're now dealing with lithium, and we're now dealing with nitric acid. So combining those bits of knowledge, the salt is therefore going to be called lithium nitrate. Yeah. Potassium, no different. It's the trigger word again of azu. This time the metal is potassium though, and the acid is sulfuric, so it's going to end with sulfate. So it makes potassium sulfate. Yeah. Third type of reaction. As I said, there are 4 that you have to be familiar with. Okay, so the first one there was MASH. So we've gone over that. Second one was the azu, so the alkalis, and this one we're focusing on metal oxides. Now the key thing here is that metal oxides are usually described as bases. Okay, alkalis are a type of base which are soluble in water. So metal oxides aren't always soluble. Okay, and in fact often they're not soluble. So if you think about that distinct difference, it's not the pH that's going to be different between a base and an alkali, or the nature of what reaction it undertakes. It's just the fact that you're looking and focusing on whether it's dissolved or hasn't dissolved. Okay, so whether it's soluble or insoluble. Okay, so metal oxide there. Now the colour is an interesting one here because they're hardly ever white. So the metal oxide colours derive from what metal is present in it. So copper oxide is jet black, for example. Iron 3 oxide is red, it's the colour of rust. Magnesium oxide is white, but that's because it belongs to group 2. Group 1 and group 2 will always make white solids. I'm not sure a teacher's ever told you that, but anything from group 1 or group 2, its compound will automatically be white. Okay, so the colour, depending on what metal is present. So there is no rule here where it says that it's a colourless or that it's all white. Depends what's present, okay? So metal oxides can be described as bases, hence the trigger word here I told you earlier was bazu. Base plus acid makes salt plus water. There's a slight disagreement in our school because my colleague says abzu. So I say bazu, he says abzu. Who's to say who's right? But it's the same letters. As long as you are consistent in teaching yourself that trigger word, doesn't really matter. Okay, so abzu, bazu, doesn't really matter. So like alkalis, the products is always a result of a neutralization reaction. So you'll have something that is eventually honing in on that central point of 7 or getting closer to 7, making it neutral. Okay, so example there, you've got sulfuric acid and iron oxide. Well, that means that it's going to be iron sulfate, okay? Because yet again, you're looking for the identity of any metal and you're looking at what the acid you've added to it is, okay? So it's the same rule as always. You can see there that you've got the same series of acids and the same series of endings or suffixes, so the endings to the words, okay? So there's just a few examples for you there. which is copper oxide. Now, copper oxide is a very common reaction with sulfuric acid. It's the method of making the most beautiful blue copper sulfate, which I'm another thing that you might have come across from quite early on. I don't know why it is, but lots of people are familiar with copper sulfate and that distinct blue color that it represents, even from year 7 onwards. Okay, so copper oxide is a black solid, but when you add it to sulfuric acid, it makes it makes copper sulfate, which is that bright blue solution you might be familiar with. Okay, sodium oxide, same sense. You're looking for the metal, you're adding the correct ending, which in this case would be chloride. Okay, so it makes sodium chloride. Then you got iron 2 oxide. The reason I'm emphasizing that, and I'll just quickly go to the cheat sheet. I have to say that really carefully, otherwise I sound like I'm saying obscene things. In your exam, you'll come across a bit of a quirky fact, I suppose, is that one metal, which is iron, has 2 possible ions. So you'll come across that as iron 2 or iron 3. Okay, it's the only one that appears twice as the same symbol. So you have to be very careful that you use the right one within your answer. So in this case, because it stated that it was iron 2 oxide that was used as the reagent, it will automatically make iron 2 nitrate. Okay, and if you started with iron 3 oxide, which is also quite common, you'd have made iron 3 nitrate as the product. So whatever ion of iron you have is going to be the ion of iron in the product. I sound really Welsh when I say iron. Okay, so it's a case of look for which one to use. Okay, there'll be 2 in the table of ions you're given. Just be consistent. If it doesn't tell you as a hint, okay, so unless stated as iron 2, that's actually quite rare that they give you an iron 2. The most common one is iron 3. Okay, so unless they tell you, it's probably a safer bet to go for the iron 3 than the iron 2, I would say. Okay. Then moving on to the final one, which is the metal carbonate. Now, this one, yet again, makes a product that you can visually see being made. So a student adds a solid carbonate to an acid. If you are a triple award student, so you do the separate courses, you'd have studied a unit in year 10 called limestone. So limestone is an example of a carbonate or a metal carbonate, primarily calcium carbonate. Okay, so in this question, the student adds a solid carbonate to an acid and the sample fizzes. If it's a carbonate, say it in your head. If you're in the middle of a test, don't say it out loud, obviously. But if it's a carbonate, what sensible gas am I familiar with that could be? Carbonate, carbon dioxide. Okay, so it's a case of think. Am I kind of saying the answer in my kind of reading of the question? If it's a carbonate, it will make carbon dioxide. As I told you earlier, the identification step for a carbon dioxide production is lime water, and the lime water turns cloudy. Now this, I'm not sure whether you're familiar with, and your teachers told you, there are only 2 allowed words. You're only allowed to call it cloudy or milky. As a WJC examiner, I'll tell you that is one of the rules that, yet again, we're kind of handcuffed into. We're not allowed to take weird explanations or descriptions of lime water's appearance. It's either cloudy or milky. Nothing else is allowed. We're not allowed creamy or whitey, or I've had lots over the years. Okay, stick to the 2 that are allowed, which is lime water will turn milky or lime water will turn cloudy. Those are the only 2 you're allowed to use. Okay, so a carbonate, okay, it tells you that it's going to make carbon dioxide gas. It also makes a salt. Again, always makes this salt. It's the common denominator, okay, and it makes water. So as I told you earlier, the trigger word that my pupils are taught is cascu. Don't ask me why we went on that order, but it's called cascu. Okay, so carbonate and an acid will make salt. carbon dioxide and water. Okay, so the only way you can tell the difference between, if you get bubbling and you've added something to an acid, it could be one of two things. It could be a metal, or it could be a metal carbonate. However, both of them make very, very different products, i.e. one will make hydrogen gas, which will explode with a pop. One will make carbon dioxide, which will turn lime water milky. So the only way to tell the difference is by testing the gas you are supplied with. Okay, so takes you through an example there. As always, that is the suffixes or the endings that you need to be familiar with. So hydrochloric, chloride, etc. I'm sure you'll be saying that in your sleep tonight because you've heard me say it so much, but it's good to have it ingrained in your brain. Okay, so a few examples for you just to test, and I'm keeping a conscious eye on the time because I know I've got a few minutes left. So you've got sodium carbonate, hydrochloric acid. Makes three things. That's the thing here as well. Don't forget it makes three things, not just two. Okay, so you've got the products there. The reason I'm not dwelling it too much on is because I need to move on to a classic question. This is what I would say is the most standard, box standard, shall we say, question that an examiner, doesn't matter, these have been around since I was in school. Now that's a long time. I keep telling my kids last century, and actually it's true. Okay, so last century, these questions were still existing. Okay, so the type of question would be, if you have a central acid and you perform kind of box standard reactions upon those things, what will you make? So you can see there that the core thing is a nitric acid. That automatically tells you that all salts will be nitrate salts. Can't make any other sort of salts, okay, because it's nitric acid. Tells you, if you follow, it is often this kind of structure of a 12 o'clock question, a 3 o'clock, 6, so it goes up, down, left, right. If you follow the one going upwards, it tells you that it's magnesium ribbon. That tells you that this is going to be the question on MASH. Okay. It tells you down alkali. So that tells you automatically that that will be the azu equation you're looking at. Highlights here that it's a metal oxide, which I told you was a base. So this is going to be the bazu. Okay. And then it tells you that it makes a gas D by adding a powder. Well, we know that only two things make a gas: a metal, which isn't a powder, and a carbonate. Okay, so that tells you that this arrow is therefore going to be the Cascu arrow. So if you look at the question they're asking you, what is powder C? Well, powder C made a blue solution of B. So it's a bit of a kind of treasure hunt, I suppose. You have to work out what B is as well. But if you look at it, B was copper oxide added to nitric acid. So we know that B is therefore going to be copper, and because it's nitric acid, copper nitrate. Okay. Then, if you know that it was a copper salt that was made in C, we know that C is therefore going to be a carbonate because of the Cascu decision. And therefore, we think that C must be copper carbonate. Alkali E, well, if you look at it, it made sodium nitrate. I told you earlier in the presentation that an alkali is going to be a hydroxide. Putting that information on the fact that it's making sodium nitrate and it's an alkali being added, we can then establish that alkali E is likely to be sodium hydroxide. Okay, so gas A we decided was MASH, so that is going to be H2. And if I just quickly pop down that it goes pop. And gas D was the Cascu, so CO2, and that is milky lime water. Okay. Now, I appreciate that that was probably a bit of a swift journey through the classic reactions, and the rest of the PowerPoint I didn't get to is no less important, don't be wrong, but we couldn't have fitted it all into one brief session. So if you are doing higher in particular, it would well be worth your time to just browse the rest of the PowerPoint, okay, once you're at home on your own and you have time to do so, just to do the second bit of this unit, which is basically how to prepare salts, okay? So hopefully that was of some benefit to you. We'll see how it goes. Hopefully I will see you again in a few weeks' time when I will be presenting again, but I will be present next Wednesday as well, where I'll be able to answer your questions when Mr. Black takes back the reins. Okay? Thank you.